Okay, so today we want to, and by the way, there's some examples, some more kind of crazier examples we could come up with, but I trust that you saw enough of these in the homework last night that you feel good about them. We're still in the same section, but today we want to like swap out for a geometric series here. We'd like to consider a simple geometric series like this, like we did yesterday. In fact, I think we did this one maybe. That exact example. And I'd like to have us all consider what it would even mean to replace 1/2 everywhere by x. And the question would be like, does this even make sense? Does an equal sign even belong here? Like that would be like my question is, does this even make sense? We have like an infinite polynomial on the left side of degree infinity, whatever. And on the right we have a rational function. What? I mean, it's still certainly true that for this even to make sense, we require that r, which in this case is x, be between -1 and 1, exclusive, right? In order for it to converge. But like understanding this expression and why this actually like maybe makes sense is like maybe the entire subject of today's lesson, and perhaps the rest of the unit too. This idea that we can represent not just like an infinite series with numbers as a single expression or a single number, but maybe an entire function that's a huge long polynomial as a single function that's got a series expansion. This is your first encounter maybe with a power series, and that's our name for these when we stick an x in there. And we'll examine this exact function here some more in a second. Yeah, Michael.
Is it true that for any function x that you can have it converted on a set interval?
Yeah, again, that particular question is pretty loaded and is the subject of this, basically the subject of this entire unit is like what functions can we give power series representations for, and how do we do it? And when do they apply would be the other big question. Yeah, exactly. And how good are they, and how fast do they approach the thing that we're looking at, and things like that. That's like the entire subject of this unit. So, yeah. Yeah, a power series is, I'm so glad you asked. A power series is something of the form, and this is important because a lot of people think like any infinite series involving like x's at all is a power series. Well, no. For us it means the thing we just viewed. It means something times x to a power plus something times x to a power. The first one here we might call, and this is the example we just looked at too, the power series centered at 0. But you could also have a series like this, which we'll call a power series also, where really that corresponds to just kind of like a shift to the right or left. So we could call it centered at x equals a. And we'd call a the center of the expansion of the power series. You have to like kind of really plumb the depths of what that last expression even means for our lives.
It means the
1 plus, really? Is that polynomial equal to 1 over 1 minus x? That last one. You don't believe it? You can start investigating on your calculator too. I'll show you a picture. I realize there's not the notation up there. Is it all clear? wildly unusual here. Okay, so let's return to this expression that we just looked at a second ago. In summation notation, you might write it this way. I didn't have that earlier. But this is what we just claimed. We said that this just follows almost immediately from like our pre-calculus result when we talked about a1 over 1 minus r. That's what this is. First term is 1 divided by 1 minus x, which is the common ratio. And we already talked about, like, yeah, I mean, this does seem to work. If we plug in x equals 1/2, it seems to be a true statement. And again, it's not just like it approaches 2 is what it comes out to be, right? If x is 1/2. We would say it equals that, right? Again, this is demanded by the fact that it's geometric, right? So we want r, which is in turn, right now r is x. So we want x or r to be in absolute value less than 1, strictly less than 1. So here's a picture of 1 over 1 minus x, the rational function. It has an asymptote over here, right, at 1, which I'm not showing really on the picture. Here's y equals 1. I think we'd all agree that that's like not a great approximation for this function, but I will have to say it does agree with the function at a particular value. And what's that value? Yeah, and just by virtue of the fact that we've constructed this way, of course it will always agree with the function at the center of your expansion, whatever that center is. We might call that, even though it's terrible, we might call it the constant approximation. Y equals 1 is the constant approximation to this function at x equals 0. The next one is familiar to you, right? 1 plus x is also known as the linear approximation, or the, what else do we call it?
The derivative of x equals 0.
It's not the derivative, but it's close, right? You'd use the derivative to find it. It's the
Tangent.
It's the tangent line, right? Or the linearization. Or the first order approximation. We have like 1,000 names for it, don't we?
We do.
All of these are good names for that we've been using this year, haven't we? Now we might, I think we minimized this last one, but now it's like a really good thing to say maybe. First order approximation is a good way to say it. It's the tangent line approximation. So did you see what we just did there? I mean, that's kind of crazy. In order to verify that that's the tangent line, if I asked you to find the tangent line to this function at x equals 0, you probably wouldn't have done this. You would have taken the derivative. There would have been a derivative involved. You would have taken the derivative. You would have evaluated the derivative at x equals 0. You would have found the x and the y coordinate at that point, and then found the, right? What do you think the next thing I'm going to put up is? Maybe the quadratic approximation, right? So notice that this matches the function at x equals 0. It actually matches the, and this is, I don't want to give too much away, but it actually matches not just the function and its first derivative, but also its second derivative. You could check if that's true, but right now we'll just say that it's kind of like the best parabola fit for this function near 0. We'll just say it that way for now. And of course, as you keep going, you see that we're getting a better and better picture, right? Here's the third order approximation and the fourth order approximation. And feel free, it's easy to do on your calculator. Feel free to type this in and see it get better and better and better on the interval -1 to 1. Yeah.
That's just the sum.
Huh?
That's the sum.
Yeah, this is just increasing the.
Adding more.
Yeah, ideally, this becomes equality when you have an infinite number of these terms. And I think I'm convincing you of that by the picture, too. Does it look like if we were to do all the way up to x to the 11th? Go ahead and try it, on your calculator. You'll get something that, especially for values close to 0, that's almost indistinguishable. And in the limit, it is completely distinguishable. They are the same function, the left and the right, completely the same. We should always stop to appreciate how wonderful that is. Like, that's incredible. Okay. Okay, I don't have too much more to say. Let's just like play around with this now, this idea, because there's lots to say now about this. Like, here's some infinite series. Can I come up with a function that it represents? I think so. If it's geometric, at least. We're still gonna like stick with geometric series mostly here today. So what is Can you come up with a function that this represents? What's the r value? What do we need? We need the a1 value and the r value, right? So what's a1 here? If you plug in 0, you get 1. And what's r? 3x. Okay? So we can write down the sum, that is the function that this represents. Here it is. It's, someone tell me. Go ahead, David, say it louder. Well, yeah. The series is 1 plus 3x plus 3x squared, which is 9x squared, plus, etc. True. And then what's the actual function representing this? 1 over 1 minus 3x, yeah? And again, you could run the same, we won't do it, but you could run the same experiment. You graph this on your calculator, graph each one of these as it gets better, and see that in fact that we're right, that they're the same, because this still seems a little crazy in our mind. You could do it, but I promise it's true. Except we should put a little bit of a caveat on this. By true, we mean when. When is this true? When what? When this is, when r is what? Between -1 and 1, right? Don't we still require that r be between there? So when is this, what window would we have to view this function on and this power series on in order to witness it converging? Yeah, we solve this and we get the interval, and this is maybe not that great, you know. You might be like, actually this is really cool, but doesn't seem that powerful because it only works like in a very, very small neighborhood. Increasingly we're going to encounter functions though that converge everywhere even, which is even cooler. But these, we do have some limited range where this applies. Outside of that range, it really doesn't make sense to us. So I think we've done, that's called the interval of convergence. So this is only true for x, 1/3, in between those two values. All of this just comes from your knowledge of geometric series. It's just we've never really taken it this far and put x's in there, right? Let's do another one. Again, is this a power series? Is it geometric? Can we represent this as a function? What's a1 and r here? Let's see if we can write that down. What's a1? If you plug in 0 here and here, I mean, yeah, we still get 1. I just come out and say it. We don't always get 1. On these two examples, we do. Okay. R is interesting, isn't it, here? Yeah, it's negative x minus 2, or negative x plus 2, however you want to say it. Is that okay? Isn't that what we're multiplying by each time? I mean, you could combine these. This is, if you want to rewrite this sum, it's negative x minus 2, just rules of exponents to the n. I just decided to write it that way, but do you agree that the thing that we're multiplying by each time is negative x minus 2? Just to be clear, if you wanted to write this out, what would it look like? It'd be, the first term is 1, the next term is that times x minus 2, and then x minus 2 squared minus x minus 2 cubed, etc., right? Okay, so just to be, that's centered at 2. So what's the power series representation? Excuse me, what's the function representation? Someone else that I haven't heard from, maybe. Give it. A1 over, how does it work? You want to give it though? What is it going to be? 1 over yeah. What is it, Elizabeth? Yeah, 1 over 1, we can go ahead and say 1 minus negative, whatever. Okay. And actually, we can clean that up even more, can't we? What would that be? That'd be 1 over x minus 1. And we still need to talk about where this actually makes sense. But do you agree with the algebra so far? Beautiful. Okay, so we do still need to think about where this applies. It's not a trivial question. We have to like actually do this again, right? And think about the algebra over here. So we'll return to that in a second. But I think we've done the, any questions about this piece here though? Yeah, Michael? Or no? Okay, so we require that negative x minus 2 be between negative 1 and 1. So can you algebra that for me? That means negative 1 is greater than, excuse me, 1 is greater than x minus 2 is greater than negative 1. We multiply everything through by negative 1. And then add 2 everywhere. Have you played with inequalities enough to be comfortable with what I'm doing?
Why did you flip the numbers?
So by negative.
It doesn't necessarily be the exact same thing as how it's
Sure. Yeah. Yep. It's exactly what we want it to say, because we want this to be true. It really doesn't matter. The negative really doesn't matter too much to me, because it's in absolute value, right? So, all right. And then now we add 2 everywhere. What do we get? 3 is greater than x is greater than 1, which makes sense because what did we call 2? The center, right? So it makes sense that this converges to the left and right equally around the set. That's why it said the center is a good name for this. Okay, so let's write this just over here though. 1 is less than x is less than 3. So if you're, again, wanting to witness this happen on your calculator, you're putting this into y1 and this series into y2, increasingly better approximations. The window to view this happen on is 1 to 3, right? And that's where you'll see this converge perfectly as you increase the number of terms you use. Oh, let's go the other way. Give me the power series that this represents. If it's clear. I mean, what's going on here? Maybe this first one maybe is pretty clear. But does this look like someone having done a problem we just did? Can you go backwards on it? What does it seem like A1 is? Again, I'm even making the assumption. This is not, I just want to emphasize this. This is really not too bad because we're in the middle of this thing where we've just been talking about geometric series a lot. But later when you encounter this, you might need to recognize this as geometric. So I think it's pretty clear that this has a pretty geometric sum form to it. But just remember this experience, please. A1 is, if we're kind of going with the form here, it looks like maybe we could call A1 2 and R, yeah, or maybe just x squared, right? Because it's A1 over 1 minus R. Okay, and then it's kind of case closed. It says find the power series. So here it is. It's the first term because that's the first term plus and we multiply by x squared each time, right? Okay. Or if you want to write it in summation notation, you could do that too. How about n equals 0 to infinity 2 times x to the what? Yeah, it's x to the second to the n, right? Or x to the 2n. Okay? And also, let's say what the interval of convergence is. That is x squared we require to be in between -1 and 1. Though that's actually that's actually not a big deal because x squared will always be greater than -1. So, but let's just, I mean, this is not a, we can just think about it too. When is this going to be true? When x is between -1 and 1 again. So in the end, we do get the same answer for this one. Yeah, Michael?
Why is 2
So it's, sorry, maybe I should have written that out. It's 2, the rule for a geometric sequence is, the terms of a geometric sequence are 2 times x squared to the n. It's a1 r to the n. Or a1, if you're starting at 1, it's a1 r to the n minus 1. You know, whatever you're starting at. Doesn't matter. Is that okay? Now, we like that so much. We really do. We love what we just did so much. We're going to go out of our way to just try and make that happen. Can we make that happen here? I think we can. It doesn't take too much work to make this happen here, I think. Let's do a little rewrite on this. Can you get this into the form this somehow? I think you can. Do a little rearrange. I mean, don't laugh. Someone could do that to you. Not in this course. We won't do that to you. But I've had to do that. I've had to do partial fraction decomposition and come up with 2 series expansions for 2 fractions in a complex analysis course. Yeah, it's definitely something that could be done. We don't need to think that hard here, though. Can you just get it to start doing stuff to make this look that way? I don't know. What would you like here? A 1. Okay, perfect. I think I can make that happen. You're welcome. What would you like here? A minus. I think I can make that happen too. Are you satisfied yet? I think I am. What's A1? X. And what's R? Negative x cubed, right? Tells me this will be alternating in sign when I write the power series out. Okay? You see how the trick I pulled? And we can get even fancier than that. Okay, but so A1 is x. And then we're multiplying by x cubed each time. So that'll be x to the 4th. And then x to the 7th minus x to the 10 plus x to the 13th. Each time we multiply by x cubed as we go. Yeah? Yeah. Yeah, actually, maybe there's another way to write this, but then you have to divide through everything by 2, maybe, right? Because you still need a 1 here, right? Oh, and the other thing is, I think you're going to have powers of x cubed plus 1, and that's not a power series. It has to either be powers of x or powers of x minus or x plus a number. Yeah, but you can't have it be powers of like x cubed plus 1 or something, or x cubed. What is yours? X cubed plus 2. Yeah. All right, and then we didn't give the interval convergence, but we should. I mean, let's just say what it is here. When is x cubed between -1 and 1? When x is between negative, let's not think too hard about that one here. And let's maybe write this as a sum too, just for fun. This goes from 0 to infinity. Well, actually, maybe we could write, well, I don't know. -1 to the n. Are you okay with me writing it this way? You could write it a couple different ways, but how about x to the, this just takes care of the signs for me. But this is to the 3n, right? By the same logic as before. But then we also have to multiply by an x everywhere, right? So how about that? Try that on for size. Will that work for us? Study what I wrote and make sure that you like what I wrote. I think that's maybe my favorite way to write this. I don't know. This got really deep fast, right? I mean, we're all we did was like poke the concept a little bit of that geometric series, and here we are. Let's do another one. Can you make this again? Can you make this look like a1 over 1 minus r? If you want something in life, make it happen, right? Whatever that thing is. I need an idea from someone. Just someone, please. Just have an epiphany. Just do it. Have an epiphany. Have it. Yeah, let's divide by 5 on the top and bottom. I like that idea, and I think then that like the game is up. Right. Are we good then? All right. Well, that wasn't. We can finish this problem, but it's no longer that interesting to me. That was the fun part. Okay. So you do that one. Let's not. I don't really care to. This one I do love, and I do want to think about. So I think I'd just like you to stare at this, and again, maybe just have an epiphany here. This doesn't seem geometric at all. There is a hint waiting for you. Maybe that was too much, though. I shouldn't have said that, maybe. I don't recognize this function as being geometric, but I do recognize maybe its derivative. I just happen to know its derivative looks really nice to me. The work is still not all done for us. Just for fun, let's innocently consider the derivative. Let's innocently consider the derivative, which is what? 1 over 1 plus x. Even the way I wrote it was really nice, wasn't it? Had it ready for you. All right, well then let's just write the power series here. It's for this. Let's just be clear. This is not the answer to the question, but let's write it out. Is it clear? It's negative x is the, so it's 1 minus x plus x squared minus x cubed plus etc. Which is, here, I'll write it over here actually, which is, how do we write that in summation notation? Yeah, we could write, and actually I'm going to separate off the coefficient here just to make it clear. I think that's the story right there. N goes from 0 to infinity, right? So this is, let's just say it again. This is not the answer to the question. So, say it again, Josh. Maybe we should integrate everything, right? Term by term, both sides. You know what I'm saying? You know what I'm saying? A little of this action. Okay? That looks like fun to me because when we do this, we get f. Now, there is a little bit of a footnote that we're going to have to add on this, so we'll come back and be clearer. And when we integrate this, we should get the original function back. I mean, integrating this function gives us ln of 1 plus x. So this should, and this is 1 over 1 plus x. So when we integrate it, we'll get ln of 1 plus x, the thing we want. Right? Let's write it over here too. 1 over 1 plus x. So when we do that, we get ln of 1 plus x. Okay, here it goes. Integrate term by term with me. X minus x squared over 2. Keep them coming, Elizabeth. It's got kind of a nice look to it, doesn't it? Maybe you could even write the rule. What is it? It's not geometric. Let's just say that. It's not true that when we multiply by one thing, we get something the next term. There's no common ratio. So what is this? What is the rule? Yeah, well, we still have these alternating signs. It's negative 1 to the n times x to the n over n, going from 0 to infinity again. Just check me on that. 1 to infinity. Well, yeah, we have to. It's okay. It's okay. Everything's fine. And then I have another question here. We still need yeah, I have another way of saying that maybe. Could we have integrated this? Because this is a little weird the way we just wrote that. Though completely correct, and I'll put it in a box. Here we go. I want you to think about, could we have taken this expression and integrated it? Keeping in mind that x is the variable of integration or differentiation. Could we have gotten it that way? What would we get? We'd get n going from 0 to infinity. This is just a constant, right? I just want to make sure that's why I'm saying we're clear on this. We're integrating with respect to x. Negative 1 to the n is a constant. We get what? X to the n plus 1 over n plus 1. Is that the same thing we have? It's just a little index shift, right? But then we have like a term missing too, maybe? But maybe we can think about why that happens. Yeah.
Why do you keep putting like a negative 1 to n instead of like a negative x?
Only because at every opportunity, I really want to emphasize that what we have here really truly is a power series. And by power series, I mean something times x to a power. And if you have like all sorts of other garbage, it might not be clear that that's what's happening. So I just want to make that utterly clear that yes, in fact, we do have powers of x here. No harm if you put the negative 1 in there. But. So that would be another great way to write this too, for sure. And you're welcome to integrate this term by term over here or do it over here. It works great inside of a summation notation. We could do that too. Yeah.
So if you put the -1 and proceed to the end, and your first term is n-1, isn't that?
Oh yeah, yeah. We don't like this anymore, do we? Down here. Down here is what you're saying. Yeah, exactly. So now we have to like adjust that too somehow. You know, throw a negative out front, or do you want to do -1 to the n plus 1 or something? I don't know. Fix it. Yeah, exactly. Fix it somehow. Good catch. So you're gonna say something. No,
Well, I was
go
gonna
ahead.
ask, when you integrate a sum, it's integrating the stuff in the sum, it's just integrating the stuff that has x's?
It's integrating every term in the whole sum, all the way here. The
Well,
only
I'm talking about abstractly, just doing it off the summation definition.
over
Just
here.
doing that side, right.
Yeah, we can do that. Let's just keep in mind that this is really just saying this.
So, well.
You're just doing them all at once.
So did you, like, use a rule to go from the summation notation to the other one, or did you?
To get this?
Yeah, or
No,
did
I
you-
just looked at this and wrote it, right? Just like you guys did.
So it's not like you can integrate the sum and come up with another explanation.
Yes, you can. This is a fine answer too. Right? That's what I just did. I said if you look at the form of this and integrate it, and then just, that's what I was challenging you. Are these in fact both right? And the answer is yes. They mean exactly the
Jennifer
same.
Thompson, please come to the attendance office. Jennifer Thompson, please come to the attendance office.